Hey guys, Buildzoid here, and today we're going to be taking a look at another one of the KingBank DDR5 kits that I've been sent. This time a 6800 CL34 24 gigabit Hynix MDI kit. It's single rank because it's 24 gig sticks, and I'm running it on the Maximus Z790 Apex Encore again with the 14900K. So, now this is a 6800 CL34 kit, so I will also be testing it on some 4DIMM boards. I'm not sure which 4DIMM boards yet, but I do want to test it on some 4DIMMers because at 6800 CL34, the XMP is low enough that it'll actually work on 4DIMM motherboards, at least Intel 4DIMM motherboards. So, yeah, it's not really like 6800 CL34 is not really something you'd want to be running on Ryzen because on auto settings you would end up in 2-to-1 mode and that's not good. Obviously you could clock it down or you could clock it up depending on like we'll cover that in a separate video. But I do want to test this also with some like Intel 4DIMMers because yeah, 6800 CL34 is low enough that the XMP should actually work. Which is not true in my experience for, say, even 7200 rated kits, depending on what motherboard you're using and how unlucky you get with your CPU. Anyway, also you can see I have a fan on the memory, right? If you're going to be pushing DDR5, you should put a fan over it as far as I'm concerned. Just helps with stability, and that's kind of that. So let's take a look at the settings. So what I ended up, also you'll notice that I do have the oscilloscope monitoring. So this has been monitoring the core voltage of the CPU the entire time that the system's been running. And you can see that it hasn't gone over 1.46 volts because of the voltage limit that I'm running as well as the undervolt. And this is on the latest 129 microcode. Anyway, let's take a look at all of the stress tests that I've run as well as the performance. So I ended up pushing this kit to 7600 CL36, and the reason it's CL36 and not a lower CAS latency is because I decided that, so with the previous KingBank kit, I was running it at like 1.65 volts on the VDD, and that was to get mainly to just get the CAS latency down to CL32 because that was a 7600 CL36 kit, and so it was like, I wanted to, at least I wanted to push it a bit further, but this is a 6800 CL34 kit, so for me here, the priority was just getting from 6800 to something higher. And I decided that, it would be somewhat interesting to show like reasonable voltage settings instead of just like smashing VDD into everything. So this is just 1.45 volts. These memory sticks do use a Richtech PMIC that's unlocked, which is why we can run them at 1.45 volts. Because if you have a locked PMIC, that maxes out at 1.43, so that's not a concern with these sticks, because yeah, it's an unlocked PMIC. And so I'm running them at 1.45. And in terms of the actual timings, well, 7600, 3646, 3844, 2T. Very similar timings to basically what I was running on the ADI-based kit in the previous video, including the TWR. So at this point, I'm starting to think that the weird, like, the TWR behavior that I was complaining about in the previous video might actually be tied to the CPU or something, but I need to do more testing on that. Because my priority with this was, like, I wanted to get stable settings first and then, like, work from there. Well, stable and tight settings. Because obviously if I left everything on auto, it would also work. Well, mostly work. Yeah, so I wanted something reasonably fast and stable. And so I do plan to do a little bit more testing on this. Like, mainly I want to see if, like, because this right now is very stable, right? We have, like, 4 hours of Y-Cruncher, because I was running into some errors with like a slightly different timing configuration, like when I had this at 62. And I think there was some other adjustments as well in terms of timings, but yeah, I was running into errors in Y-Cruncher that were like an hour in. And so I ran 2 instances, like 2 sets of Y-Cruncher, just to make absolutely certain. Well, it's not like you could obviously run it even longer. So it's not like absolutely certain, but like if it was erroring out, at around an hour previously and it didn't error out in 4 hours, it's probably good now. Also, it passed like 11 hours of Karhu, almost 8 hours of HCI mem test, right? So Yeah, I would definitely consider this like daily stable, at least to like my personal stability standards. Um, I don't know that I would necessarily want to run this on like run these kinds of settings on a workstation, right? Like if you're doing long renders that take multiple days to finish kind of stuff, but for anything less than that, yeah, I like for my personal use, I would totally tolerate this level of like stability validation. But yeah, so that was sort of the last timing adjustment I made was like bumping this up to 62. But at the same time, there was times where I was testing TWR pre below 90, and so it might have been that like actually it was like a TWR SG problem and not a TWR pre with this kit. The other kit, I definitely narrowed it down to like TWR pre complaining. So I still want to do a test where I lower TWR pre and then it'll probably crash Y Cruncher is sort of what I'm expecting to happen. Um, in which case, yeah, this like CPU maybe just doesn't like low TWR, which doesn't really make a ton of sense. But if RAM made sense, I wouldn't, have to make these videos all the damn time. So, and I wouldn't have to like retest everything constantly if RAM made sense. Um, so yeah. Now, in terms of the overall performance, this is a little bit slower than the settings that I was running on that A-die kit that I have from KingBank. And the reason for why it's a bit slower, so the A-die kit that was getting about 7.14 seconds in PyPrime, this is getting 7.27. Also at XMP settings, this was over 8 seconds of runtime for PyPrime, so quite an improvement compared to stock, but still a little bit slower than the A-die based memory. And the reasoning for that is very simple. We're at the same speed, but the A-die kit was at CL32 with a TRCD of 44. Also, the TRFC was lower, TRDSG was lower, and TRFC per bank was also lower on the A-die kit. And the thing is, 24 gigabit M-die just doesn't do any of these like generally doesn't do these timings as tight as 16 gigabit A-die does. So that's actually expected, is that if you're at the same clocks, M-die is a tad slower. Though I'm also not helping the kit here. Like obviously the A-die kit was also getting run at 1.65 volts, which meant that I could push the cast latency lower. But timings like TRCD don't really scale a lot with voltage, so I think even if I bump this to 1.65, TRCD would probably not get below 45. And TRFC actually just wouldn't get better at all. That just actually wouldn't change. TRDSG is also like hard stuck at 10. If you set this to 8, it instantly locks up the system. So yeah, there's nothing that can really be done about that. That's just like 24 gigabit MDI things. Sort of the main, but like the main benefits to 24 gigabit MDI is that it generally clocks higher if your CPU doesn't suck massively. And it's also like easier to, well, yeah, it'll clock higher if your CPU is capable of higher clock speeds more easily. And it has more capacity, right? Like if you just need more than 32 gigs of RAM, MDI gives you 48 gigs of RAM, which is beneficial for certain applications, right? Like, so, yeah, that's kind of the situation, is that like clock for clock, MDI is generally a bit slower, but on the flip side, you can sometimes clock it higher. This is not one of those situations because I like my success rate with getting anything above 7600 to work on Intel CPUs is 0. I've literally never had anything above 7600 work. So that's why we're at 7600 even with an M-die kit. Even though the A-die kit also maxed out at 7600, like I just don't want to deal with the intricacies of trying to get anything higher than this to work. So anyway, yeah, so that's sort of the performance situation here, is it's a little bit slower in PyPrime. I could make like a bit more of an improvement could be made by just bumping the VDD voltage higher, but then obviously the cooling of the memory sticks becomes potentially more important. If your memory sticks run too hot, you'll run into like refresh interval issues. That's like the main thing that you'll run into, is that like hot running memory doesn't, like you can't spend as much time between refreshes or you'll lose your data. And that usually only becomes a major concern if your memory sticks are above like 60 degrees Celsius. But yeah, that is something to keep in mind. And the other thing is actually TRCD scales with temperature. So potentially, if you bump the memory voltage really high and then the memory sticks end up at like 70 degrees or something, your TRCD might get worse in terms of minimum stable TRCD. But yeah, if you have a fan on DDR5 sticks, like the funny thing is with the level of cooling I have here, which is really just like an 8, it's not, it's like a 92 millimeter fan, I think. It might be an 80. It's an AMD stock cooler fan. But yeah, with one of these, even like 1.45 volts, 1.65 volts, they actually run at very similar temperatures. Like this is just under 50 degrees, whereas at 1.65, it would run like 52, 53 degrees. So like it's not a huge, cooling requirement change, but it is something to keep in mind. Anyway, we went over the stress tests, right? Like HCI for 8 hours, Carhu 11 hours. Anything else? I think that's it. So now we're going to just go into the BIOS because to take a look at the settings. Oh, also, you'll see no errors, and hardware info was running the entire time that I was running the stress tests. And you want to watch for this because, yeah, Intel CPUs won't always crash a memory test, but they might throw like Windows hardware errors. So, yeah, that's like you wanna check for those as well if you're stress testing your memory. Also, here's the SPD profile. I do kind of wish the memory kit came with like a 6000 expo option instead of a 6800 expo option, but for Intel systems that is not a concern. So yeah. Oh, also if you want to check what PMIC your memory kit has, you can do that by unticking sensors only for hardware info, and then it'll give you the full system-like report. And then in the full system report, you go to memory, you go to one of your memory sticks, and then you scroll down until you get to here, right? And you can see which PMIC you have. So, yeah. And this one is unlocked, so we can go above 1.43 volts on the voltage. So, yeah, I think that covers everything that I want to show you in the OS. So now we're going to restart and take a look in the BIOS. So just quickly, we're going to go over the actual CPU settings. I'm just using the Intel Extreme, like default settings Extreme profile with LLC level 6 and sync AC/DC load line turned on. So that makes sure that the AC/DC load line actually matches the VRM load line. And then for the internal CPU power management, I'm just using the, ASUS like defaults to the 400 amp limit, so that's just fine. But I have the VR voltage limit set to 1440. Which is 1.44 volts, which is how, like, the thing is level 6 LLC has a little bit of overshoot to it. So with level 6 LLC and a 1.44 volt limit, we're getting like peaks of 1.46, which is just fine, right? Like that's way below, like Intel's own limit with the 129 microcode is 1.55 volts. So we're like 110 millivolts below that. So not concerned for the health of the CPU with these settings whatsoever. And then I also have a 0.07 volt negative voltage offset through the adaptive mode for SVID. So a slight undervolt. Now, you could, like, this CPU could probably tolerate a bigger undervolt than this, but when I'm running memory stress tests, the last thing I want to deal with is CPU instability due to a overly optimistic undervolt, right? Like, so yeah, that's why I'm just staying at like a 70 millivolt undervolt instead of something bigger than that. Because this gives a decent little performance uplift. Also, it doesn't really make the CPU run any cooler because for Y-Cruncher VT3, like the CPU still just runs at the power limit. But it does make the other two tests a little bit more power efficient. Anyway, now for voltages, we have System Agent at 1.25 volts, which is perfectly fine. And at speeds like 7600, like depending on the motherboard you have and the memory speed you're trying to run, you might have to do a lot of fine tuning of System Agent. But with the Apex Encore, this is actually what the voltage that this motherboard defaults to at 7600. And it seems to work just fine for me. So I've not, bothered to like try tune this up or down or anything, because this works at 7600. At higher speeds, probably doesn't work. But I'm not gonna concern myself with running higher speeds on Intel CPUs any longer. I have found it to be a massive waste of time, and that's just kind of that. It was like, yeah. So 1.25 on SA, because at 7600 it works, and it worked with the 8i kit. It works with this kit. So I'm not gonna, I'm not gonna fix something that works. Anyway, VDD 1.45, you can see I have the high voltage mode enabled, because if you don't enable this, the max voltage that you can set is 1.435. For the settings that I'm running here, the 1.45 isn't actually necessary. This is just to like show that, yeah, this PMIC is unlocked. Or it's like mostly to show that the PMIC is unlocked, because I think at 1.4 it was a little bit unstable. So maybe with like 1.42 it would have been enough, but usually when tuning memory voltages, I go in increments of 50 millivolts anyway, so not really a concern as far as I'm concerned. VDD-QTX is at 1.35. This is also what the motherboard defaults to. I've just like locked it in. And this is also the same VDD-QTX that I was using with the 8i kit in the previous video. And then memory controller voltage is at 1.4 volts, which is perfectly safe, because this is the same voltage that you have for like DDR4, right? So if you run DDR4 with a 13th gen or 12th gen CPU, and your memory kit, or like a 14th gen CPU, and your memory kit has like a 1.45 volt XMP, yeah, that's the memory controller voltage for DDR4. So yeah, like honestly, with the memory controller voltage, I wouldn't be concerned about it, even if it was at like 1.6 volts or higher. There's just generally not any reason to actually do that, because it doesn't help stability with DDR5. Anyway, so that's it in terms of the voltages that I've actually tuned here. And now let's take a look at the memory timings. So primaries are 36, 46, 16, 38. I did not check if a lower TRCD WR would work. It's not really like, I think the actual like register limit is probably 8. I'm not sure if it has to be 8, but it might be. But the thing is, TRCD WR, it helps a little bit with performance for like pi prime benefits from it a bit. But there's not really a reason to try push this super duper low, because generally speaking, your memory performance isn't write limited. Right? Like usually you need to read a lot more than you need to write to the memory. So like with Hynix memory sticks, you can usually set a lot of the write related timings really, really low, but on the flip side, it doesn't really do that much for performance. So, I don't see like a point in actually trying to minimize this. Because yeah, like especially for like a daily setup, I don't see a reason to try minimize this. TRP is at 38, which is pretty typical that with like Hynix A die, M die, you can usually run TRP pretty similar to what your cast latency can do. In my experience, is usually like 2 or 4 ticks higher than cast latency. But I have heard of some cases where you can actually run it below cast latency. I've not run into that myself, but yeah, Silicon Lottery things. Similar is actually the same is true for TRCD, is like TRCD in my experience is quite different from memory kit to memory kit. Like a variance of, like you can have multiple 8i kits, and some of them will do like 2 ticks higher TRCD. Same for M die, is like the TRCD. Like some kits will do, say, at 7600, you might have some kits that'll do 44. You might have some kits that'll do 46. Or 45. Or I don't think you'd ever get anything so bad that it would need like 47 for stability. I guess if you got really, really lucky, you might find a kit that does like 43 at 7600, which would be kind of insane. At least in my experience, that would be kind of insane. But yeah, you might run into something like that. Anyway, so yeah. So TRP at 38. which is just pretty typical Hynix things, though M-die usually does somewhat looser TRP than A-die. And by that I mean 24 gigabit M-die, because there's also a 16 gigabit M-die, and that behaves nothing like 24 gigabit M-die. Okay, they should not. They're completely unrelated. They have, well, the one thing they have in common is that they're manufactured by Hynix, and that's about it. Anyway, now TRAS at 44. This could potentially maybe go a little bit lower than this, but M-die usually has a higher TRC limit than A-die does. And on Intel, you can't actually set TRC, which is fine. Like, that makes actually more sense to me than like AMD's setup where you have a separate TRC timing. Because the way TRC works is like the minimum delay between a activate command and a pre-charge command. Oh no, it's minimum activate to another activate. So the way TRC is like the way Intel memory controllers basically have TRC anyway is that they just add the TRP timing to the TRAS timing, and that gives you your effective TRC. Yeah, with M-die, probably, like, I think at 40 it might actually stop being stable. Whereas with A-die, you might be able to push it a lot lower than this. The thing is, TRAS also isn't that important to performance, but it does gain performance. Like, lowering TRAS, like, I wouldn't use, like, the XMP TRAS for this memory kit is like 100 and something. So going from 100 to like 44 is actually a pretty big performance benefit, especially for a, you know, very memory sensitive benchmark like Pi Prime. So yeah, but also if you push this too low, obviously it'll cause instability. Then the command rate is set to 2n, which we're on DDR5 in 2-to-1 mode, so that actually works to a command duration of 4 clock cycles, but that doesn't really matter, because that's just like how DDR5 works, so we don't really have to concern ourselves with that. Now, TRDL and S, these are at 10 and 8. This is one of the bigger differences between A-die and 24 gigabit, like 16 gigabit A-die and 24 gigabit M-die, is that 24 gigabit M-die has a really high TRDL limit. So setting it to 8 at 7600 instantly locks up the system. You can't, like, you just can't do that, generally speaking. And as you go higher and higher in memory speed, this timing does tend to have to get looser and looser and looser. Whereas with A-die, you can often run like 8, or at high voltages, you can also run less than 8. Yeah, this is 24 gigabit M-die, so 10 for stability at 7600 is a necessity. So, yeah. Also, it's worth noting that ASUS actually defaults to this if you're like tuning like an M-die kit on this motherboard. So the board actually sort of takes care of this for you. But also, like, yeah, you can't set this below 10. And I did briefly test 12, but there was no reason to actually run it at 12. That was just like me trying to chase down some instability. And, you know, M-die is sort of known for having a high TRRDL limit. So I tried 12 to see if it's like maybe a TRRD issue. It wasn't a TRRD issue, right? You saw the stress test pass with a 10. So yeah, 10 is perfectly fine. So 10, TRRDS at 8. I didn't bother to check if this would work at 4. It doesn't really make that much of a performance difference with DDR5 because the burst length on DDR5 is 8 cycles anyway. Yeah, like if you wanted to experiment with that, you could try like pushing it lower. It's just not really going to give you a huge performance benefit because it basically just allows the memory controller to shuffle commands around a bit differently. Like it's like a scheduling benefit than an actual like direct throughput increase. Unlike on DDR4 where the burst length is 4, so if your TRD is anything higher than 4, you get like significant performance loss. But DDR5 that doesn't apply. Anyway, so TRFC2 and same bank, I have at 640 and 420. ASUS actually defaults to 640. And what's kind of interesting is like if you go much below, like a little bit below 600, it's no longer stable at all. So yeah, like that 640 is actually pretty close to the limit for this memory kit at this voltage, at this speed. Same happens with TRFC same bank. I tried pushing it a bit below 400, and at that point it's just completely unusable. So I ended up like 400 might have worked for passing stress tests, but like 20 ticks of TRFC is just not going to make that much of a difference. So I set it to 420. 620 might have actually also been viable for TRFC 2. But again, like 640, 620, they all kind of perform the same. Honestly, if I was trying to do something in terms of like more like improving the refresh performance, I'd probably look at like cooling the memory sticks more and then trying to push the refresh interval higher, because that would be a lot like safer than trying to, micro optimize the, like that would give you probably, yeah, that would probably give you somewhat better returns on like time and effort invested in terms of performance gains. And like less risk of like instability, right? So like I think actually at the temperatures that the memory sticks are running right now, 100,000 might be viable for refresh interval. Um, but it also like even that isn't gonna like massively change performance at this point. So yeah, and if your priority like when it comes to daily memory settings, I like using the system. My daily system, I like using it, not running stress tests on it for like a week. So yeah, I personally wouldn't like maybe if you had the memory sticks on water cooling, then sure, go wild with the refresh interval. But if you're just air cooling them, um, 65,000 works even at kind of high, like rather high temperatures, and it's really not that much slower than like 100,000. So yeah, that's what it is. Read to pre at 16. 12 might work. This was a I guess unintentional side effect of me trying to hunt down the instability that turned out to be TWRRD. Um, yeah, 12 might work, so I might check if 12 will work. Though it's worth noting that read to pre, going from 16 to 12, like PyPrime will probably get a little bit faster, but PyPrime is so insanely sensitive to memory performance that it really skews your perception of how important various timings are. Anyway, TFAW at 32 because neither of our TRDs are less than 8, right? So there's really no reason. Like I could set TFAW to 16, but that actually wouldn't do anything in this scenario. So at 32 it stays. CKE at 8. I didn't bother to check lower values because they sometimes don't work, and CKE isn't super important for performance. DRAM write latency at 24. This could potentially go lower. I didn't test. Yeah, I didn't like test 20, but this is a pretty typical Hynix thing, is that you can push the cast write latency like ridiculously low. Unfortunately, it doesn't really translate into massive performance gains. It just kind of looks neat. So, yeah. Now, in the memory training algorithms, you'll notice that everything is on auto. If you have a better memory controller, it's worth turning on the turnaround, like round trip latency training. Turning this on will give you somewhat lower memory latency. However, it can also cause instability. And I am tired of dealing with instability on Intel CPUs, so that stays on auto. Now we get to the tertiary timings, or also known as the back-to-back timings, because with these control are like the delay between two read commands and that kind of thing. So this is something that should actually work even on the Hynix A-die. On the A-die kit, I wasn't running the tertiaries this tight, because again, I was trying to hunt down, like with the A-die kit, I was trying to hunt down some instability that turned out to be the WR time, like the write recovery timings. And then I didn't bother to fix the like read to read, tighten the read to read timings again. So I left them at 16 for same group. So also, it's worth noting that for all of these timings, odd values just get rounded up to the nearest even value. So if this was 13 is functionally the same as 14. They perform the same, they have the same stability, they are the same, because the memory controller literally cannot do odd tertiary timings. But anyway, so let's go through these. So at 7600 with most A-die kit, well, with M-die or A-die, you should actually be able to run tertiaries like this, where it's like 14.8, 18.18, 12.8. Again, the writes are faster than the read operations. Just Hynix things. For a lot of other memory chips, it's actually the other way around, where the write operations are slower than the read operations, and it's like, say, Samsung memory chips, I think, do that. And then Micron memory chips also do that, where like write operations are slower than read operations. But Hynix chips are just like really good at receiving data or something. So yeah, you can have very fast back-to-back writes. And then write to read transitions, same group, 64, different group, 44. And this is probably like the limit for this kit, because I did try 62 and I also tried 60, and I was getting like late instability in Y Cruncher. So and by late, I mean like an hour in, it would error out. So 64, 44, and I wouldn't try to tighten this further at this speed. At lower speeds, like 7200, these should go proportionally lower than they are here. Yeah. For 7600, this seems to be the limit for this memory kit. Though I didn't check if different group would go any lower than 44, which it might. So that could be worth tuning a bit, but I don't think it'll go much lower. Like, I don't think it'll go below 40. So yeah, then we have a bunch of timings. You know, I have mixed feelings about the way Asus organizes their back-to-back or tertiary timings, because what they do, like, most motherboards will group all of your like read-to-read timings. So like read-to-read same group, read-to-read different group, read-to-read different rank, read-to-read different dim. They'll be all together in a nice block of like 4 timings. Asus does this, where they give you all of the single rank timings first, and then you get all of the dual rank timings. So these are all dual rank timings, so those are all set to auto, because this is a single rank setup, and these are not relevant to the anything of the system. They don't affect performance, they don't affect stability. Though I have seen some motherboards which get kind of weird about memory training if you actually adjust these. So, yeah, that's just like funky Intel memory controller things, because this is a single rank setup, and these timings literally do not apply to any of the scenarios that the memory here operates in. So anyway, that's that. Then we get a bunch of timings that I've just left, like these timings that I've left on auto, because they don't really do anything, because I have power down disabled. And then we have WR pre, which is at 90. So I do want to do some more testing on this, because it doesn't really make sense to me that this would have to be 90. But I already ran into this with the 8i kit in the last video, where it was like it just kept erroring out at like an hour plus of Y Cruncher, because I was trying to push TWR pre below 90. WRPDEN is at 90. This is mostly just so that like the memtweakit utility reads out to TWR value. This timing isn't actually used in the configuration that I have here. TREFI X9 is at 255, because that's the maximum this can be. Yeah, you want this maxed out for best performance, and it doesn't, like, maxing it out doesn't affect stability. So, like, a lot of motherboards will actually default it to 255 for you. Now, the reason I said the TWR PDEN doesn't actually do anything is because if we go into the miscellaneous timings and we scroll down to our power down settings, you'll notice that power down is disabled, and the memory controller idle is disabled, and the self-refresh is also disabled. And this basically makes sure that the memory sticks are always ready to read and write, instead of ever having the I/O circuitry turned off, which is basically what power down is just it puts a part of the memory stick to sleep to save a little bit of power. But this is a desktop. DDR5 memory sticks don't pull that much power. DDR5 memory controllers don't pull that much power. If this was a laptop, then obviously this would not be a great idea, because laptops run on battery, but this is a desktop. The RGB LEDs on this motherboard probably pull more power than the power down settings for the memory sticks do. I mean, like, the memory sticks having the I/O circuitry turned on instead of having it turned off when it's not in use. So I see absolutely no reason to bother with having power down turned on. And I really appreciate that, like, Asus gives you all, like, this much access to the power down settings on their motherboards, because a lot of other motherboard vendors, you won't even have the option to disable power down. You know, like it's just not in the BIOS, which is kind of frustrating. Though I think some of them might like turn it off for you, but just not, you know, show it in the BIOS, which is still kind of annoying, right? So anyway, um, fast boot is enabled, so we don't like the memory doesn't train every time we boot the system, which is nice because that means the system boots quickly. Though when you're tuning memory, it's probably best to actually have this disabled so that the because on some motherboards you won't get your timings applying if you don't disable this. Asus actually handles that just fine in my experience, so not a massive concern. Though I've also sometimes you like want to force the system to retrain if you're, especially if you're changing like voltages and stuff. You're gonna want to disable this so that the memory controller actually like retrains for whatever voltages you're running. Um, because otherwise you can sometimes end up in a situation where you're changing voltages and the stability is like not reacting to the voltages the way it should be because the memory controller is on like settings for different like trained on different voltages, and so when you change the voltages it doesn't like, and if it doesn't retrain it doesn't have the effects that it should have. Luckily, I didn't have to deal with any of that with this setup here because it's just 7600 again, and I already know for sure that like 7600 with the voltages I'm running here worked with the A-die kit, so there's not really any reason it shouldn't work with the M-die kit. Um, so, yeah. That's it for the BIOS settings. Yeah, so 6800 rated kit, clocked all the way to 7600. Not really surprising because like it is 24 gigabit M-die, so you know it's not exactly like I'd be more surprised if it didn't work at 7600 to be completely honest. So um yeah, so hopefully you found this video somewhat interesting if not particularly useful. And big thank you to KingBank for providing the memory sticks. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below as well. And yeah, that's it for the video. So thank you for watching and goodbye.